Hi there, my name is Sullivan and today I'm going to be walking through the Floyd-Warshall algorithm. A brief introduction, the Floyd-Warshall algorithm is a dynamic programming algorithm that is used to solve all pairs shortest paths problems. Below you can see an example of a graph and the solve distances matrix, but we'll get into what that means a bit later. A little bit of background on the algorithm. As previously stated, the Floyd-Warshall algorithm is utilized on directed and directed weighted graphs. The Floyd-Warshall algorithm was created by several authors, with most of their published findings coming out in 1962, with its current form credited to Robert Floyd. In order to make it easier to understand the content we are covering, here are some useful definitions. We begin with a directed graph, which is a set of vertices and a collection of directed edges. Each directed edge connects an ordered pair of vertices. All pairs shortest paths problems deal with finding the shortest graph distances between every pair of vertices in a given graph, and an adjacency matrix which represents a graph G with an n by n matrix M such that each entry of the matrix is a Boolean value of 0 or 1. And we'll see this played with a little bit in the output of the Floyd-Warshall algorithm. Now, an overview of the algorithm. Floyd-Warshall simultaneously calculates the shortest paths for all vertices in a directed or weighted directed graph. This differs from algorithms that accomplish similar things like Dijkstra's algorithm, which calculates the shortest path between only one pair of vertices at a time. Floyd-Warshall's output is a distance matrix, that is, a matrix made up of the distances between each set of vertices. This matrix can be represented by an adjacency matrix. It is important to note that the output is the lengths of the shortest paths between all pairs of the vertices. It does not include or return any information regarding the paths or their order. However, it is possible to slightly modify the algorithm to also include that information. There are also other slight variations on the algorithm. One of those variations can be used to find transitive closure of a relation. However, we won't be diving into those versions of the algorithm right now. Here's an example of a write-up for the Floyd-Warshall algorithm. This isn't the only way that you can do this, and there are multiple different ways that you can actually write out this algorithm. However, this particular example deals with prepping our matrix M and then also doing the actual calculation of Floyd-Warshall, which you can see in the triple nested for loop on the bottom of the write-up. To further demonstrate what Floyd-Warshall could look like, here's a sample implementation using Golang. This code will yield the following results. On the left, you can see our input matrix, and on the right, you can see the associated output from the code that was just shown. To go more in depth into the Floyd-Warshall algorithm, we're going to look at a little bit more in depth the implementation that we just saw. Here you can see a really basic program implementing Floyd-Warshall in Golang, while also creating a little bit of a driver program around it. So we have our input graph here. This is the same input that we showed on the previous slide. We have our actual algorithm here, which is the same algorithm implementation that we showed on the previous slide. And then we print our input matrix, a new line, and then our output matrix, and this is our little helper method for printing. This actually does the Floyd-Warshall algorithm calculation. We've got our nested for loops here. And so if we go and we run this, we'll see our input matrix and then the output matrix, the same that we showed on the other slides. Again, this is just a basic implementation, but another way to see it in real life. Now we're going to get back to our slide presentation and look more closely at the complexity of this algorithm. So the complexity of the Floyd-Warshall algorithm is big O v cubed time. So v is the number of vertices of our graph. This is the case since Floyd-Warshall uses 3 nested for loops in order to calculate each shortest path. The storage complexity of the Floyd-Warshall algorithm is also dependent on v, but tends to be negligible, given that the algorithm doesn't utilize overly complicated data structures. Most often, the storage complexity can be represented by big O v squared, given we need our input and output matrices, which will both be n by n matrices. So this concludes my walkthrough and presentation of the Floyd-Warshall algorithm. Here you can find my sources. This slide deck also includes the sources that were used in the written portion of this assignment, and you can find a link to the paper and the slide deck used in this presentation in the video description. Thanks so much.